So this is my list of suggestions. Um, you want to use these enough that you get used to them. So one of the most useful things that you can do is change everything to sine and cosine. Um, Clearly, you want to keep your eyes peeled for things that you recognize. So when you look on your formula sheet, everybody, at the Pythagorean identities, there's sine squared plus cos squared is equal to 1. There's another Pythagorean identity that says 1 plus tan squared equals secant squared. There's another one that says 1 plus cotan squared equals cosecant squared. Look, you don't have to memorize all those, but you need to recognize that all of them contain the number 1 and the square of a trig ratio. So if you're working on something and you see 1 and cotan squared, that might be a clue for you to go to your formula sheet, because there's an identity there that might contain them. Try factoring if possible. We're going to run into many examples where factoring is going to be a very, very good thing to do if you have fractions that are being added or subtracted. We never want a over b plus c over d. We want a single fraction all the time. And the last piece of advice I get, if on your journey things start to get more cluttered, more confusing, more messy, then you've taken the wrong path and you need to go back to the beginning and try a different path. So, Reagan, you had asked about which one?
6C.
Okay, so I'm going to look at 6C. And the intention here today in seminar and class is that we're working on these. I may end up spending the whole close to 2 hours going over stuff on the board, and I don't mind doing that. But you need to also be working on stuff. So, I mean, if I'm working on a problem and you're going, no, I get this, you should be working on another problem. And just because I said today we're doing this doesn't mean once the bell rings at the end of our regular class today that you're done with this stuff. You got to practice it. So, 6C. So we have tangent over cosecant. Tangent of x over cosecant of x. I'm pointing out something to you that may not be that important to you right now, but this is a single fraction. And there's nothing being added in the numerator or denominator or subtracted. This is going to become important in a second. So I'm going to rewrite everything in terms of sine and cosine. Tangent of x is sine of x over cosine of x, because that's one of the quotient identities. Cosecant of x is 1 over sine of x, because that's one of the reciprocal identities. And I'm going to explain this the same way I did for that other one, Reagan, but I'm going to bring everybody else into what we were talking about. This line right here is what separates the numerator from the denominator. It's very easy for us to say that, oh, this is a complex fraction. But what does a complex fraction mean? A complex fraction is considered complex because either in the numerator or in the denominator, there's another denominator. So, there's many ways I can communicate this idea to you, but basically this and this, they're trouble. They got to go. We don't want many denominators within the numerator or within the denominator. So, these need to go. That's what it really boils down to. Because if we can get rid of many denominators, the fraction is not complex. It's simple or simpler. So how can I get rid of the cosine of x? Well, I can multiply the top of this and the bottom of this by cosine of x. And I want you to notice where I wrote those cosine of x's. I mean, I don't want to complicate things here further, but cosine of x as a fraction is cosine of x over 1. So I'm keeping it lined up. Because when we multiply across the top and the bottom of fractions. Let me get rid of this. That would get rid of the cosine of x. But we would still have the sine of x that's highlighted that needs to go, which would mean I would also have to multiply the top and the bottom by sine of x. And the reason I think this is obvious, but we need to discuss the algebra rules here. This has nothing to do with trig right now. The reason I'm multiplying both the top and the bottom by, say, cos of x, even though I only need to get rid of a cos on the top, is because cosine of x over cosine of x is 1. And I'm effectively then multiplying the whole expression by 1, so I'm not changing its meaning. It still has the same value. So now what you do is you focus exclusively on the numerator. Don't look at the denominator right now. Just look at the numerator and ask yourself what would cancel within the numerator. And the answer is what would cancel would be this cosine of x over this cosine of x goes away. And I say look only at the numerator because I don't want you doing something potentially silly like canceling a cosine of x on the top with a cosine of x on the bottom, because then you're just going backwards. Now we look exclusively in the denominator, and you can see that there's a sine of x over a sine of x. And now what you need to do, and this is it can be a visual challenge for people, is you need to rewrite everything that's still there. So we still have that main fraction line, and on the top we have sine squared, because there's a sine of x times a sine of x, and on the bottom we have a cosine of x. Now, that may or may not be the answer. Is that the answer? It is. But I want to let everybody know, and even if you're working on one right now, just swivel your attention up here for a minute for me, please, that on an exam, if I give you this as a multiple choice question, it could be that the answer is actually tan x sine x, because sine squared of x is sine x times sine x, and it's over cos x. This sine x over cos x is tan x. And this is the frustrating thing that students encounter at this stage. Trigonometric expressions can have many different appearances even though they're all the same. I mean, not all trigonometric expressions are the same. You get my drift though, right? That we could literally have 50 different expressions, but they all are equivalent to each other. Other questions? Go ahead, Ian. 4E? So we have cosecant squared of x minus cotangent squared of x. Now, I want to spend some time with this. What would happen if we converted everything to sines and cosines? Because that's a suggestion, right? It's not what I would do, but I have a little more experience with this, so I can see, and you can't yet, when I take a step down that road, I can see a couple more steps ahead of where I am than you can. You know, you're still looking down because you don't want to stumble. I'm kind of looking ahead, and sooner or later you will start looking more and more ahead. But if you start with the sine thing and cosine thing, or a very technical description of it, if you start with the idea, Ian, that we can write everything as sine and cosine, and by the way, for the most part, you have an extra one, okay. For the most part, it's going to be possible to do that. It's going to be very complicated at times, but it's possible. This becomes 1 over sine squared of x, because cosecant and sine are the reciprocals. Minus cotangent is cosine squared of x over sine squared of x. Did I do this one yesterday? No? Okay. Now where we are, Ian, is we have fractions. But we don't want fractions to be separate. We want to put them together using a common denominator. And we lucked out here because these are both over sine squared of x. Oh, I did do this one with somebody after class. That's why it's still in my head. And I'm at that stage. Are you okay with that, Ian? Okay. Now, although I do believe we did have this conversation yesterday, it just wasn't with this problem. That is drilled into your head already, I hope, that if you see sine squared plus cos squared of an angle, x in this case, it will be equal to 1. But if I subtract sine squared from both sides, I have this. And what that means, it's not relevant to this question, Ian, but what that means is if I ever see this is my eye, if I ever see that, then I can think it's cos squared of x. All right, so if I'm working on a problem and I see 1 minus sine squared of x, I can just, in the next step, write cos squared of x. In other words, this identity of sine squared plus cos squared equals 1 is a second identity of cos squared of x equals 1 minus sine squared. And it's a third identity of sine squared of x equals 1 minus cosine squared of x. All I'm doing is I'm rearranging this top identity by subtracting cosine squared of x. So I know I'm putting a lot of pressure on you. There's a burden here. It's piling up. But you need to keep your eyes peeled, which means open. Keep your eyes peeled for this, because you know it's 1. Keep your eyes peeled for this, because it's cos squared. And cos squared is simpler than 1 minus sine squared. Keep your eyes peeled for this. Well, that's what we have over here. We have 1 minus cos squared on the top of this fraction. So this becomes sine squared of x over sine squared of x, which is 1. Just go ahead.
The way I did it was I saw that 1 minus cos x, or I saw that cos x.
Cos squared of x?
Cos squared of x could be seen as 1 minus sine squared of x.
And then you substitute that in for cos squared?
Yes.
That'll work.
But then I got 1 minus sine, which would be negative sine.
No, it wouldn't. 1 minus sine squared. And it's squared. You keep saying sine, but it's squared, and that's important. That does not give you negative sine squared. It gives you positive sine squared, because you're subtracting. Negative 1 times 1 is negative 1. Negative 1 times negative sine squared is positive sine squared. I mean, the other thing you could have done here, everyone, is I see cosecant squared and cotangent squared there, and there is a Pythagorean identity that contains those. I mean, there's 2 Pythagorean identities, and I just can never remember these, so I have to look. So, for example, where are we? Cosecant squared is 1 plus cotangent squared. Cosecant squared is 1 plus cotangent squared minus cotangent squared. Boom, 1. Cotan squared minus cotan squared is 0. You know, and you could potentially as well, for cotan squared, put in 1 minus put in cosecant squared minus 1. There's other paths you can take. The thing, and I've mentioned this with my calculus students, and they'll recognize this idea. The thing about math is it doesn't lie. As long as you're following the rules of math, the path that you choose still gives you the right answer. You just may want to, push your way through the brambles in the bush to get home, or you may want to just walk along the sidewalk. Sometimes the sidewalk is hidden. Other questions? Go ahead. 4F, certainly. So for 4F, we have sine of theta. I like theta better. The x thing is a little problematic at times, and then we have plus cotangent of theta, cosine of theta. Again, so far, Marcel and everybody, the basic strategies for these introductory questions, the ones that we're working on right now, is to rewrite everything as sine and cosine. So I rewrite cotangent of theta as cosine over sine. But now what I have, and I'll just rewrite this again, is sine of theta plus cosine squared of theta over sine of theta. This is important, and I'm teaching you algebra at this point in time. I'm teaching you about rational expressions. The fact that there's a multiplication in here means we really have one fraction with that second part. So I can take the cosine times the cosine and write it over the sine times the 1. And now what I have is two fractions that I need to bring together. Does that make sense? So I bring things together by looking for a common denominator. The lowest common denominator is the thing that we can convert both of those denominators to, which would be sine of theta. And in order to get this first fraction of sine of theta over 1 to be over sine of theta, I need to multiply the top and the bottom of it by sine of theta. So what I'm going to get is sine squared of theta over sine of theta plus cos squared of theta over sine of theta. And then I can put these together as an entire fraction of sine of theta in the denominator and have sine squared of theta plus cos squared of theta in the numerator. I'm just curious, Marcel, would you potentially go from here directly to there? Yeah, I think most people would, but some people need to write them separately first. And we're almost done. You just now need to recognize that sine squared of theta plus cos squared of theta is equal to 1. So we end up with 1 over sine of theta, and that could be your answer, or it could be that your answer is cosecant of theta. Yeah. 5A? Certainly. So now we get to things where you're factoring. And I want to be clear here. In question 5, we're still warming up here. Question 5 is telling you what to do. So normally you would see on an exam, what is this equal to? But here you're being told to factor, and I'm going to explain to you why, even though if we converted everything to sine and cosine, we will get home, we will get to the answer. Factoring will be quicker. Well, it depends on how you look at it. There are two terms here. There is this term minus this term. And although it's secant and sine, algebraically, this is no different, everybody, than that. I want everybody to just contemplate what I wrote there and see how it connects to 5a. 5a is secant times sine squared minus secant. I have a times b squared minus a. If I said to you, factor this, you would factor an a out. You would factor the a out and be left with b squared minus 1. So here we can factor a secant of x out, and be left with sine squared of x minus 1. Does that make sense so far? Okay. Now, unfortunately, I'm going to start loading more on your shoulders because I've told you that you are expected to know cos squared of theta plus sine squared of theta equals 1. You are expected to know that cos squared of theta is 1 minus sine squared of theta. You're expected to know that sine squared of theta is 1 minus cos squared of theta. But now, and I don't know that you have to memorize these, I'm just pointing out to you that there's many ways to rearrange this very, very important identity at the top of the right of the screen. I could write negative cos squared of theta equals sine squared of theta minus 1. I could multiply, there's a number of ways to imagine this. I could multiply that asterisked equation by negative 1 and get negative cos squared, and then get sine squared minus 1. So in my mind here, what I'm getting at is that I've already told you, man, keep your eyes peeled for this, right? 1 minus sine squared is cos squared. This is not 1 minus sine squared, though, is it? It's the opposite of it. It's sine squared minus 1, which means that it is negative cosine squared of theta, and or of x. And I've made a horrible mistake here by not having my x here. Okay. Does that make sense? If you are not comfortable with that, there are all kinds of ways for us to work around this. One of them is to say, and I know that there will be people that want to do this. I'm just going to finish my thought and then we'll take a little break. One of the ways is to say, so I'm a student and I'm looking at that and going, oh man, if it was 1 minus sine squared, if it was 1 minus sine squared, then I would know it's cos squared, right? Well, how do I make it 1 minus sine squared? Factor out a negative 1. The sine squared becomes negative. The 1 becomes positive, and then you can put cos squared in. And I'll finish this problem in just a second. Okay? Okay, welcome back. One way or another, you need to know how to get to this point, right? And you're okay with that, I think. See, it's at this point in time where I think we can write everything in terms of sine and cosine. And many of us will see that when you write secant, like even the thought of what you're going to do with secant leads you to seeing one step next beyond where you're at, that you will have a cosine canceling. So if secant is 1 over cosine, and then we have negative cosine squared of x, let's not forget what negative cosine squared of x means. It means negative 1 times cosine of x times cosine of x. I don't think you need to write it this way. It's over cosine of x. I'm just pointing out why you were allowed to cancel a cosine out of the top and the bottom. And we're left with negative cosine of x. Other questions? Ian?
Sorry.
Okay, think about the question before you commit to it. Yeah. 4D. Okay. So we have secant of t times sine squared of t times cosecant of t. The nice thing about this one, Reagan, is that we have these three things that are being multiplied together. And whenever you have things, everybody, that are multiplied, it's a free-for-all in canceling. The whole purpose of putting things together when you have separate fractions is so that you can get free-for-all is the wrong word maybe, but you can get the ability to cancel things. If I rewrite everything in terms of sine and cosine, secant is 1 over cosine. So secant of t is 1 over cos of t. Then I have sine squared of t. And again, look where I wrote it. Look how I wrote it. It's not, I mean, if you write this, it's not wrong, but it makes it difficult for a student to see what's going on, and it makes it really difficult for me to explain what's going on. So we have times sine squared of t, and then we also have times, and even look at where I put the times symbol. Everything's lined up nicely. I'm not all over the place. And I think it's helpful. Cosecant of t is 1 over sine of t. And again, since we're multiplying, this goes back to rational expressions in 20-1. Since you're multiplying, you just multiply across the top and multiply across the bottom. So this line that I've written here, Reagan, I didn't need to do that. I could have said, well, the secant is 1 over cos. The sine is sine squared. The cosecant is 1 over sine. So I could have done that, but I know from experience, if I just write that out and say it, people go, well, wait a minute, what just happened there? I think this middle step, the first thing I wrote, is important. Anyway, the same kind of thing here, and you're not going to write this every time. I'm just doing this to explain to you why what is about to happen can happen. Sine squared of t is really sine of t times sine of t. So these cancel, and you're left with sine of t over cosine of t. And again, I believe that you should be able to do that without writing it out as I did on the right. But this is the explanation as to why they cancel. And by the way, you should immediately go, oh, that's tangent of t. That shouldn't even be, if you're at the stage where you're going, what is that equal to again? Then you have a long way to go yet. Other questions? Yes? 6G. Certainly. All right, Adrian, let's take a look here. 6G. 1 plus cotan squared over secant squared. So what is going to happen in many instances with this stuff is I will show you how to do a problem and you will go, that's it? It becomes so simple. And part of that is because I have more experience. But it ultimately boils down to us following the steps that we have here. Now, there's two things that we can do here with this question. We could write everything in terms of sine and cosine, but I see 1 plus cotangent squared of x. And I think on your formula sheet, I'm going to open up a formula sheet here so I can refer to it. I'm pretty sure on your formula sheet 1 plus cotangent squared is equal to something, but I'm going to check because those are the identities that I don't remember. Yeah, it is. Look at that. Center of the screen here. 1 plus cotan squared of theta is cosecant squared of theta. So when I see this question, on the top, I have 1 plus cotangent squared of theta, or x, over secant squared of x. So I'm going to write that as cosecant squared of x over secant squared of x, because on my formula sheet, that's an identity. 1 plus cotan squared equals cosecant squared. Did I remember it right? It's equal to cosecant squared? Okay. Now, this is just a little more compact. Now what I'm going to do is write everything in terms of sines and cosines. So cosecant squared, in the numerator of this, cosecant squared is 1 over sine squared. In the denominator, secant squared is 1 over cos squared. And, I've exaggerated the main fraction, but I really think it's important that you understand where the middle of the fraction is. Now I have things that need to go. Right? This has got to go. This has got to go. They're trouble because they're creating within the numerator fractions and within the denominator fractions. So how do I get rid of those things? I'm going to multiply the top by sine squared of x to get rid of the denominator of sine squared of x in the numerator. But that means I have to multiply the bottom by sine squared of x as well. There are other ways to handle this, but what I'm showing you is a utility device that will work for any fraction that's complex. I also need to get rid of the cos squared of x in the denominator, so I'm going to multiply top and bottom by cos squared of x. Very carefully look at what cancels. What cancels in the numerator are the 2 sine squareds. What cancels in the denominator are the 2 cos squareds. So what am I left with in the numerator? Like out of this whole thing, what's left? The only thing that's left is cosine squared of x. And in the denominator, the only thing that's left is sine squared of x. And you should probably recognize that as cotangent squared of x because cosine over sine is cotangent. So the answer is cotangent squared of x. Is that okay? Other questions? Yep. Certainly. Let's take a look at 5b. We can't write everything as sine and cosine because it already is. And there's one and only one way to figure out what this is, and it's to factor it. And I'm going to take you back to grade 10 and grade 11 just for a moment and say to you that if I had x squared minus 16, that factors into x plus 4, x minus 4, the product of the two conjugates, because x squared minus 16 is a difference of squares. Okay. What if I had r to the 4 minus 16? Well, r to the 4 is also a perfect square. It's the perfect square of r squared. So I could factor r to the 4 minus 16 into r squared plus 4r squared minus 4. But r squared minus 4 is a difference of squares. So this factors into r squared plus 4, and then r plus 2, r minus 2. And you encounter that in grade 10, and then we talk about it again in grade 11. The bottom line here is that this sine to the 4 of theta minus cos to the 4 of theta is a difference of squares. Sine to the 4 of theta is the perfect square of sine squared of theta. So we can put sine squared of theta here and here. Cos to the 4 of theta is the perfect square of cos squared of theta, which we can put here and here. The answer to the question is sine squared of theta minus cos squared of theta, because this is 1. Now, could we, I don't know what the answer is in this handout, but could we say that's the answer and be correct? Yes. Could we say this is the answer as well? Certainly, because you can factor sine squared of theta minus cos squared of theta as a difference of squares one more time. Does that make sense? Okay. Other questions? Yeah. 6. E? E as an elephant? Okay, thank you. Sorry about that. So we have cosecant minus sine. There really, when you go through that list of 4 or 5 tips that I've given you, the only thing that we could do is to rewrite everything as sine and cosine. What that's going to do is open up the door to one of those other strategies. Because when I write this as 1 over sine of x minus sine of x, and look at again how I've written it, the sine of x is really sine of x over 1 mathematically, so I've made sure to write it that way. I'm left with this statement. But now I have fractions that need to come together. Okay? And the common denominator here would be sine of x, because if I multiply the top and the bottom of this by sine of x, they will both have the same denominator. And I think you might see exactly where this is going. We're going to get 1 minus sine squared of x over sine of x. And I think I had asked you earlier, we can put them together as one fraction, right? We could write them as 2 separate fractions first and then bring them together, but I'd rather not. It's not that I'd rather not. I don't need to. Do you recognize what 1 minus sine squared is? Good. 1 minus sine squared is cos squared of x, because sine squared of x plus cos squared of x is equal to 1. So our answer is cosine squared of x over sine of x, and we're done. Okay. I just want to throw this out here, everybody. How many of you recognize that this is the same as saying that? So you're starting to see it. You're starting to, I don't know if you remember, but yesterday I asked, how many of you see that this is equal to something? And it was like one person kind of sheepishly put their hand up because they weren't even sure. And I said, the next time I ask, more and more of you will see these things. This is cosine of x over sine of x. Well, the cosine over the sine is cotangent and then times cosine. Other questions? Yep.
1 plus cosine x squared. 1 plus cosine squared x. What is that equal?
What is it equal to? 1 plus cosine squared x.
Okay, then.
So there's nothing we can do with it. If you wanted to, there are some things you could do with it, but they are the equivalent of us stepping off the road and crawling into the bush. They're going to make things more complicated. I could put in for 1 sine squared of x plus cos squared of x, and then I have plus my other cos squared of x. So I could write it's sine squared of x plus 2 cos squared of x, but that's not a very useful endeavor. It doesn't really help us.
Could we do 6b then?
D, certainly. Did you notice that it's not 1 plus cos squared, it's 1 plus cotan squared?
Yeah.
Can I ask why you asked me about 1 plus cos squared then?
Because that's how I simplified it.
Okay. All right. So the first thing to note is that 1 plus cotan squared, keep your eyes peeled, especially for Pythagorean identities. 1 plus cotan squared, look on your formula sheet, is equal to cosecant squared, I think, isn't it? Okay. And then we'll come around and look at what happened with your strategy. Okay. So this is 1 over cosecant squared of x, which is sine squared of x. Does that kind of hippity-hop step make sense to you? Okay, so that's the answer. Now, I'm guessing then that what you did is this. And let's talk about this because, again, I think one of the reasons some people struggle more in this than others, I'm not saying it's you, but I'm just talking to the whole class, is because of weak algebra skills. So you start to compound weak algebra skills with all this new trigonometric identities, and turns into a quagmire very quickly. A mess. So is this how you started? Okay. And notice again how organized and tidy I've put everything. So I am going to have to multiply, and I will show you how to get out of this mess that you're creating. And it's not your fault you're creating it, you're trying what I've suggested, right? You're multiplying the top and the bottom by sine squared of x. Am I correct? Okay. So I guess you know what? It's not a mess. You've got a slight algebra mistake. Now, keep something in mind, Ian, and everybody. On some level, there's no such thing as a small algebra mistake, right? If you make a mistake in your algebra, it's going to be wrong. When you multiply across the top, you get sine squared of x. Based on your question to me, I'm guessing that when you multiplied across the bottom, you got 1 plus cos squared. But you don't. You get sine squared plus cos squared. Because I have to multiply the sine squared by this and the sine squared by that. I can't just multiply one of the terms. Because of that plus, that changes the nature of the multiplication. If this were a multiplication symbol in here, which wouldn't make sense because it's 1, but if it were, then you just multiply it in, and you don't have to worry about distributing it. But because it's plus, we're going to have to multiply the 1 by the sine squared, which gives sine squared of x, plus the sine squared times the cos squared over sine squared, which gives you cosine squared of x because the sine squared of x's cancel. And the bottom of this now is equal to 1. Right? The bottom is sine squared plus cos squared of x, so that's equal to 1. So we're left with sine squared of x over 1, which is what we had to begin with. Well, not to begin with, but what I had when I used the Pythagorean identity in this two-step process.
What I had done, as you pointed out, but also I just thought since the question is wanting it in sine x and cosine x, or both, that you should start off with that.
But yeah, it's good that you're pointing that out to me, but that doesn't mean that that's the best way to go necessarily. Because Pythagorean identities or other identities can very easily, I'll give you just a ridiculously over-the-top example. That if I gave you this, well, this isn't an over-the-top example at all. It's a good example. I ask you to simplify this expression. Looks pretty complicated, doesn't it? I mean, I think. Does anybody see what it's equal to? Some of you might. So could we rewrite everything as sines and cosines? Yes, we could. It's going to be an absolute mess. Could we look for Pythagorean identities? Well, certainly, because there's squareds in there. Could we factor? Well, look at the denominator. Can I factor anything out of the denominator? I can factor a cotan squared of x out of the denominator and have left cos squared of x plus tan of x. And on the top, I have cotan squared of x. I have sine of x. These are all factors. And I have cos squared of x plus tan of x. So we started off by me saying there are 3 different roads you can start walking down here. But it turns out that if you factor, you get the answer almost, well, pretty much immediately. So, and again, I think this is good that you've asked that question about, well, it said write it in terms of sine and cos, so that's what you did. So if I have a multiple choice question and all of the answers are in terms of sine and cos, that doesn't necessarily mean that's the road you want to start walking down. It just means that's where you have to end up. Other questions? Let's take a look at number 10. Tan A cos squared A over secant A. This is a goofy one. I remember this question. First of all, the fact that this is a single fraction with things multiplied on the top and on the bottom, well, there's only one thing on the bottom, makes it easy. We can do a lot of canceling as long as we follow the rules of algebra. Okay, so if we have a factor on the top, we can cancel it with a factor on the bottom. So when I write this in terms of sine and cosine, I have sine of A over cos of A. And then I'm multiplying by cos squared of A. And this is over 1 over cos of A. Does that make sense to you? Okay. Now there's two things you can do here. Did it occur to you that we could cancel on the top one of these cosines? Okay. So that gives us sine A cos A on the top over 1 over cos A on the bottom. And we multiply top and bottom by cosine of A to get rid of the cosine of A in the denominator of the denominator. And you're very confident in everything you've done. The cosine of A cancels with the cosine of A, and you're left with sine of A times cosine squared of A. And you look up dejectedly at the four choices and see that it's not there. Okay. So this is where, first of all, what I've said earlier becomes important, that there are many ways for you to disguise a trigonometric expression, right? Unfortunately, you don't necessarily know what identities to use to change the appearance to get the right answer. But you should start to see certain pieces of trigonometric expressions for what they could also be written as. For example, cos squared of A is 1 minus sine squared of A. And keep putting x, I mean A. And if we multiply that out, you're going to get choice D. The other option is, rather than, and this you might appreciate this more, rather than doing what we did and getting what I would call a simplified expression, and then trying to make it into a complicated one that we don't know what it is, what we could do is say the following. And I don't know if this logic will make sense to you, but if the question written in terms of sines and cosines is this, then if I write all of the choices in terms of sines and cosines, only one of them will match that. For example, if I write A in terms of sines and cosines, it's sine of A over cosine squared of A, right? That's the only way to write choice A with sines and cosines, but that's not what we got. And B would be written as cos squared of A over sine of A, but that's not what we got. C is obviously incorrect because it's sine squared of A, and we want a sine of A and a cos squared. With D, the only thing you could do would be to factor, and then you almost immediately see that you're going to get the cos squared of A in there. Does that make sense, Arissa? Okay, good. Were there others? That's good for now. How are you doing, Aaron? Good. How are you doing? Good. Any questions? 15? Certainly. So all 15 is asking is, if you were to verify this identity, what would you get on each side? And that doesn't mean, Arden and everybody, you have to verify it for both sides. Because if you're being told it's an identity, you're going to get the same thing for both sides. This is really a calculator question. And since, let me write this out. Since cosecant squared of x is simpler for me to work with than cotan squared plus 1, I'm going to verify it for the right side. Okay. So I need to figure out what cosecant squared of pi over 7 is. Well, what does that mean? It means 1 over sine squared of pi over 7. So I'm in radians. Pi over 7 is an angular measure in radians. Better make sure I'm in radians, and I am. So I need to take 1 divided by sine squared of pi over 7, and this is how we write it. Right? We've had this discussion before that it looks as though we're only squaring the pi over 7, but that means we're squaring the sine as well. You could, if you wanted to, do it in stages, like take the sine of pi over 7, and then square it, and then take the reciprocal. But anyway, what I get is 5.3. Is that okay? Any questions? Okay, that's on page 21. That's which one? H? T. H, J. Okay. Okay, so we're starting to get, for some of you, to the extra practice stuff. So I'm going to go over 3J here. Oh boy. Okay, so what I will say to you is that I don't think you would ever be asked this on an exam, but I want to show it to you anyway. It requires use of a particular type of factoring that we've learned and we've used, but we don't use very often. Factoring by grouping. Does that vaguely ring a bell? So what we do with factoring by grouping is we group the 4 terms. This only works, well, it won't always work, but if there are 4 terms, it has a chance of working. We group them into pairs, remembering that you have to have plus in between the pairs. In other words, you would never want to do something like this, because that negative belongs with the secant of x, not with the 1. Okay? And then what you do is you factor the greatest common factor out of the first pair, which would be secant squared of x. And we would have secant of x minus 1 left. And then what you're taught to do in grade 10 when you first learn this is then you do the same thing with the second pair, or at whatever grade you were taught this. But I have a different take on it. It's not that you factor the greatest common factor out of the second pair. You factor out of the second pair whatever you need to be left with the same thing you were left with out of the first. So we want to arrange it so that we are left with secant of x minus 1. And you can see, I hope, that we have to factor out a 1. So now when I look at this term and this term, there's a common factor of secant of x minus 1. And then we have secant squared of x minus 1. Now you might be tempted to factor this, but I believe that's equal to something in terms of a Pythagorean identity. Yeah, right here, the middle of the screen, secant squared of theta minus 1 would be tan squared of theta. Now, I don't know where this is going. I'm going to take a look at the question in a second, but it's equal to tan squared of theta. So what we have is secant of x minus 1 times tan squared of theta, or tan squared of x. I just want to take a look at what this question is asking us to do. Factor, then simplify if possible. I don't really know if this goes anywhere. We could certainly try it by doing the following. I'm not actually doing this on paper necessarily, but I might write it on paper to ask myself, what would happen if I did that? If I multiply this through, I'm going to get sine squared of x over cos cubed of x minus sine squared of x over cos squared of x. I don't think this is really in our best interest here. I mean, if this were a calculus class, we'd go a little bit further and say, well, let's multiply the top and the bottom by cos of x to get a common denominator of cos cubed. But it's just, we're going around in circles. It's going to get uglier and uglier, or it's just going to maintain its ugliness but change a little bit every time we do something. So I would say this is good. Is that okay? But again, factoring by grouping, I've never seen it on a diploma exam, and I don't worry about it on my exams. Okay. Do you have any questions? No? Yeah, of course. Yeah. Yeah, that's part of it. When you do factoring by the method of decomposition, one of the steps is by grouping.
In decomposition, correct me if I'm wrong, I haven't done it in a while. You have three terms usually.
Yeah.
You try and find the middle term by adding to them, but also multiply the product of the last.
Yeah.
And then once you do that, you write two numbers in the center around the two product numbers.
Yeah.
And then you factor out by grouping.
Yeah.
And then you get that sort of.
Yeah, you factor by grouping. Yep. Yep. But we don't factor by grouping at this level. You just use trial and error. Right? I mean that don't get caught in the factoring by grouping or decomposition. We use trial and error with that situation. Otherwise it takes too long. How are you doing? Good. Any questions? Of course, yeah. Shazmaida, did I just see your hand go up? Okay. So number 11, we want to figure out what secant of x minus cosine of x is equal to. I'm going to go through this one, and then I'm going to get everybody to pay attention because there's something I want to show you that's kind of a last resort, a last ditch effort that you can do in a question like this, okay? But it wouldn't be helpful on a written response. And again, I can guarantee you on the exam in this unit, there will be a written response that involves this kind of work. Okay, so the only thing we can really do here is to write everything in terms of sine and cosine, and secant of x is 1 over cosine of x. So I have 1 over cosine of x minus cosine of x, which is cosine of x over 1. So I'm going to find a common denominator and bring those fractions together. That's without exception, I think that's what you want to do. Well, there's probably an exception. But whenever you have two fractions or three fractions, you want to find a common denominator and bring them together as a single fraction. I can multiply the top and the bottom of this second fraction by cosine of x, creating a denominator of cosine of x in the bottom. So I have 1 over cosine of x minus cosine squared of x Cos times cos is cos squared over cosine of x. And don't, by the way, don't cancel a cosine of x right now, because then you're going back to the question, right? You want to bring these together and have 1 minus cosine squared of x over cosine of x. And then hopefully you recognize that 1 minus cosine squared is sine squared. So we get sine squared of x over cos of x, which I don't know, it may or may not be there. It isn't. But this is sine of x over cos of x. So we have sine of x times tangent of x. So now I would like to show you what you could do. And you know, you have to really believe the advice I'm going to give you here. Don't look at this as a cure-all for all of these problems, that this is how you're going to complete the exam. You will just dig yourself into a hole so deep that you will fail the exam. This is a last resort, or if you are at 100% algebra and you want to just take a break and be lazy on the odd question, this will work. One of these four expressions is the same as secant of x minus cos of x. So what I could do is I could pick a number for x. I could go in radians, pick a number, an obscure number like negative 2.6, and find what the question will give me. Don't know why there's a 1 there. Doesn't really matter. Oh, it should be divided by. And figure out what the question would give me if I used a random x number like negative 2.6. Are you with me? So when I put negative 2.6 radians in, secant is 1 over cosine and then minus cosine, I get this number. Well, that's a pretty memorable number. I think I would recognize it if I saw it again, negative 0.31. Well, let me try sine squared of x. I guess I got to slow down. Nope. You get my drift here? I can go through and I can check them all. I mean, the next one's a little more complicated. I would need brackets. 1 minus 2 cos negative 2.6, n brackets, divided by cos negative 2.6. Nope. Sine negative 2.6 times sine negative 2.6 times tan negative 2.6. There's that number that I recognize. You know, and rather than typing that all in, obviously what you could do is put in as a function. And I'm not going to look at the graph because graphs can be deceiving here with this strategy. And then put in choice A, 1 minus 2 cos x, close bracket, divided by cos x. Go to your table. Well, the two things are not equal. So then go back and replace y2 with something else. I mean, this is a strategy that if you really get stuck, it will work. What we would be doing is saying that this is in your mind, the logic, that is half of an identity. The other half is one of the choices, and you're trying to verify which choice it is. I hope that makes sense. Okay. So first of all, this bit of business at the top, Marcel, is just parsley on the fish. It's not really relevant to doing the math. It's talking about non-permissible values, and we'll come back to that later, but it's not important. So we want to simplify that. I'm going to write everything in terms of sine and cosine, so the tangent becomes sine x over cos x. And then it's times cos x. And again, I'm being very careful to align things properly. You know, I see sometimes students write times cos x. They're just very lazy about it. And you can very easily see how you might think that's sine over cos squared, but it's not. Okay. And then on the bottom we have 3 multiplied by secant, which is 1 over cos x, multiplied by cotangent, which is cos x over sine x. Now, don't dive into getting rid of those mini denominators just yet, because it turns out the coses take care of themselves. So now I'm going to rewrite what I have left. I have left on the top sine x, on the bottom 3 over sine x. I could write 3 times 1 over sine x. It's not going to matter. So now I have this thing that needs to go. Right? This has to go because it's a mini denominator. So I'm going to multiply the top by sine of x. I'm going to multiply the bottom by sine of x. Canceling these, leaving me with sine squared of x on the top, on 3 on the bottom. That's the same as saying 1/3 sine squared of x. That good?
I'm just wondering why sine isn't 0, because at the top it says sine of x is equal to 0.
Are you, let me just double check here. Are you asking why sine of x cannot be 0?
No, why isn't it in the answers? Because
I understand. It should be. These non-permissible values should technically be there, but we don't necessarily have to write them. So if we say, it's a good point. If we say we have non-permissible values that come out of sine x not being equal to 0 and cosine x not being equal to 0, it doesn't matter what we get, those non-permissible values survive. We'll talk more about that at the end of this course, and we talk a lot about that. And I think we've talked about it in Math 31 already, that even though you might be able to get rid of those denominators, the non-permissible values are still there. So it should actually say, comma, sine x is not equal to 0. And weirdly enough, cosine x is not equal to 0, even though there's no cosine there. Yep.
On the formula sheet, it says 1 plus tan squared of theta equals secant squared of theta.
Yep.
How come 1 plus tan squared of theta is not equal to 1?
You're saying on your formula sheet it says this. Your question is, why is it not instead this? Is that what you're asking? Because it can't be both, right?
Correct.
Okay, why do you think it should be equal to 1?
I put sine squared over cosine squared, or sine.
Okay, so you're not asking why isn't this on your formula sheet. You're asking why, when I work with this one, don't I get this? Is that what you're saying? Okay. Well, where would you go from here?
So that whole thing is one term, right? And then I multiply the 1 and the sine.
Just a second. That whole thing is one term. What do you mean by the whole thing,
I put
Ian?
brackets
Okay,
right there.
okay.
And I multiply it by cosine of squared.
I think we've had this conversation already today. It's the same mistake then you've made. Let's just continue.
Okay.
What would you do then?
I would distribute it properly.
So what would I write?
Cosine squared theta plus sine of squared theta. Sine squared theta.
Just a second here. Okay. You're making a mistake here that's not the same mistake you made before, but it's a huge, huge mistake. If I have that equation, I'm going to change it to 110. 110 over 2, by the way, is 55. That's my age. My age, A, equals 110 over 2. And I want to get rid of that 2. Can I just do this? I can't just get rid of the 2 and say, sorry, Mr. Way, I thought you were 55. You're 110 now. You cannot multiply something unless you multiply it by 1. So this is not a case where you're trying to get rid of it. You can't get rid of the denominators. The left-hand side has that as a denominator. What you should be doing instead here, Ian, is it's not that you're getting rid of the denominators because you have a complex fraction. That's what you would do, in which case you would multiply top and bottom by that pest. Are you with me on that? Okay. What your goal is here is to get this to be a common denominator so you can put them together. The difference here, and this goes back to Math 20-1, which for you was just last semester, right? Is we're not solving an equation where we can multiply to get rid of the fractions. What we are doing is adding rational expressions together where we find a common denominator and bring them together. So the common denominator would be cos squared of x, or theta, and the numerator would be cos squared of theta plus sine squared of theta. This line down the middle, everybody, is crucial, and I'm going to come back to that in a second. So do you see that what we get is 1 over cos squared, which is secant squared? So now why is that line crucial? Because what you're doing here, I think, is you're trying to prove that it's equal to the other side, right? And this is precisely why when you do a proof, which we will get to formally later, it's precisely why when we do a proof, you have that line down there. You work on each side separately. And I say that because, you might say, well, could I have multiplied this by cos squared and multiply the other side by cos squared? Not if it's a proof. But if you did, do you see you would have got 1 here? And if you multiply this side by cos squared, you would get 1 as well? Because this is 1 over cos squared. So the problem was you were just arbitrarily multiplying that thing by cos squared, and you can't do that.
How come we're allowed to do it when there's a complex fraction?
Because then you're multiplying the top and the bottom by the same thing. Right? I mean, if we go back now to this, if you decided to think of this as a complex fraction, you can do that. But you would have to multiply top and bottom of it, right? By the way, you will recognize that what we're really doing is converting this to a common denominator. You'll see that in a second. Because what's going to happen is you're going to get cos squared of theta plus sine squared of theta, because when you multiply here, there's canceling action happening, over cos squared of theta, which is 1 over cos squared of theta. So you were allowed to multiply stuff by a thing as long as it's balanced somehow. Now, in terms of everything we're working on, that means you got to multiply the top of the thing by that thing and the bottom by the same thing. If you were solving an equation, and I want to be very clear here, we are not solving equations here.
No, I was just wondering.
No, but let me finish my thought, because other people are listening too. If we were solving an equation, then you certainly can multiply the left side by something as long as you multiply the right side by the same thing.
Is multiplying by a common factor essentially multiplying both sides but leaving one side alone? And so you bring that multiplication that you did on the right side and moved it over to the left side?
Multiplying by a common factor. Can you give me an illustration of what you mean by that?
Well, if we multiplied top and bottom, we did that because we wanted to multiply by 1.
Yes.
And we don't want to deal with the other side right now. We want to solve that separately.
Yes.
Is multiplying by a common factor?
But what do you mean by a common factor?
Well, what we did was cosine squared over cosine squared.
Okay, so we don't have to call it a factor. Multiplying the top and the bottom by the same thing.
Is that the same thing as multiplying one side by something and the other side by the same thing?
Yes, if you were allowed to, but you're not allowed to here.
Right.
Mathematically, it's the same. Mathematically, it's valid. We do that all the time, by the way. If I have 1/3 x equals 2 and I say solve that, then you multiply both sides of that equation by 3, right? And this, again, this is, I'm in an algebra instructional mode right now. When you're solving an equation, we take that thing and we multiply both sides by it. When you're simplifying an expression, which we are here because we're working only on one side, when you're simplifying an expression, you find that balance by multiplying the top and the bottom of the expression by that thing. But if it's an equation, you can multiply both sides by that thing. Incidentally, let's see if you catch this. Multiplying the top and the bottom of one side of an equation by the same thing subsumes the other idea, which means you can always do anything by multiplying the top and the bottom by the same thing. But you cannot do any problem by multiplying both sides by the same thing. Which is why I want to finish my thought here, because I think this is a good conversation. Which is why, and by the way, do you see that same would be true for dividing both sides or dividing top and bottom? Which is why if I give you this equation to solve, I tell people, and my Math 31 students will recognize this, I tell people don't get rid of that 2. Don't divide both sides by 2, just factor it out, because it's part of the expression. Anyway, take your math home, work on it in the next day or so. Tomorrow we're moving on and looking at sum and difference identities. Then on Monday we will do double angle identities. Tuesday and Wednesday we're probably doing proofs. Thursday we are doing the final lesson. That would mean your exam is probably scheduled for the Thursday of the week after next. Or the Friday maybe. Well, we'll see. We'll see. Have a good day, you guys. We'll see you later. Can you face the other way so I can, thank you.